Hello everyone. Uh, Myself Chaitanya Kumar from Department of Electrical Engineering, IIT Madras, and we are in the seventh week. We are today going to do the tutorial session for seventh week of the circuit analysis for analog designers. And in this week, basically, we have covered the Bode noise theorem, which is an extension of the noise theorem that we did previously. And apart from that, we covered the input referred noise figures and all. So before we start practicing some problems, is there any doubts that anyone has based on the week's material? Okay, so we will start with some problems on the input referred noise and all. So the most of the part in the week, we did the input referred noises of resistors. We handled some amount of transistor noise figures as well. So we will go from there. So let's try to do the noise analysis on a transistor circuit. So I hope uh, you guys are aware of this transistor circuit called common source amplifier. So this is the common source amplifier. So we will try to find the input referred both noise as well as current for this common source amplifier. So the small signal model, first of all, we will have to write. So basically, there are two noise sources. Can someone tell what are the noise sources that are present in this amplifier? So yeah, there is thermal noise. So one thermal noise source is basically from this resistor, that is 4 kT RL, and other one is this guy that has 8 by 3 eta kT. So this is a current source. If we assume a current noise source from this 4 kT eta times GM, and this is a voltage noise source that we are assuming with this. So we will write the uh, we'll write the small signal model for this. So we have so let's assume the parasitic capacitances are open. So the transfer function from input to output. So in order to find, so we need to find both IN and as well as VN, where IN is the input referred current noise source and VN is the input referred voltage noise source. So the transfer function from both VN and IN can be for both the current and voltage we will have to write. So for voltage, can anyone tell what will be the gain from V in to V out? So basically we have V out by V in as V out by V in is yeah, correct, GM times RL, and it has a negative sign. So yeah, so this is what we have over here. So this is the transfer function from input voltage source to the output. And as far as the input current source to the output is concerned, so in this case, we had a voltage source over here, V in, and so this was the voltage transfer function. Let's call it some V of H equivalent V. And the current transfer function, if we try to find out, so I in over here. Now this voltage, so now the current source from input, now the impedance, looking in impedance, what is the looking in impedance for this network? This is infinite, right? So if some current flows into some impedance, say Z in, so the voltage developed over here will be V in is equal to I in times Z in. And as you pointed out, this is an open circuit. So Zn is equal to infinity. So the voltage developed at this node will be infinite. So output will also be, since output is minus Gm V in times RL. So since output is minus Gm V in times RL, and V in is infinity, so output will also be infinite. So we see that whatever current we give at the input, the current transfer function, that is H equivalent V of sorry I of F is equal to infinity, while the voltage transfer function was minus Gm RL. Okay, so now we need to find the output. We need to find the output volt. We need to de-energize the input sources, and we need to find the output current, or like output voltage, whatever develops due to noise, and see what is, and then divide it by the equivalent transfer function. So first of all, when we are working on the input referred noise voltage, we will consider this circuit, and in this circuit, if we de-energize the input source, what we get is the following. So we have 4 kT eta by 4 kT eta times Gm. Then we have RL, and its noise source also we can convert to current noise source. So it's 4 kT by RL. Okay, so this we get at the output. Now since V in is short circuit, so this noise source will go away from the picture. Since V in is 0, this won't inject any noise. Sorry, this won't inject any current. So what we have at the output is, so V out, the power at V out is 4 kT by RL into, where will this noise current go? This noise current will go into this resistor RL, and we will have RL square. So this will be the noise power at the output, noise power spectral density at the output, and this will be a flat noise power spectral density. And same way, this 4 kT eta times Gm will also go into the resistor RL. So it will be 4 kT eta times Gm into RL squared. Okay. Now we know the output noise power spectral density. So in order to find the input noise power spectral density, we will divide it by the transfer function square that we had as GMRL whole square. So Vn uh, the RMS value, the power spectral density, the input referred power spectral density will be 4 kT by RL. So we can cancel this 4 kT RL plus 4 kT GM eta into RL squared into 1 upon GM squared RL squared. Okay. So we have 4 kT. So we can take out GM times RL as a common factor from this thing. So what we have at the output is GMRL 4 kT by GM plus 4 kT RL upon eta. Okay. So we see over here is that the input referred noise power is proportional to GMRL, that is the gain that we get from the circuit, and it is proportional to so as we increase the value of, so GM basically can be so overall gain that we require from this common source amplifier. So we have this common source amplifier that has a GM block and a VD. So let's say you are given a top level spec that you need a gain of 4 from this amplifier. Now a gain of 4 can be achieved by multiple combination of GM and RL, but you need to see like what value of GM and RL you should choose, that even after the amplification, like depending on the value of GM or RL you choose, the noise that you get after the amplification will be different in both the cases, correct? Because see, if let's say I choose GM as 2 millisiemens and RL as 2 kilo ohms again, so in this case I will get a gain of 4, the magnitude of gain of 4. But another choice, let's say I have GM as 4 millisiemens and RL as let's say 1 kilo ohm, this thing will also give me a gain of 4. But if in the first case, this this factor in both the cases will be constant. However, since GM is higher in the this is case 2, this is case 1. Since the GM is higher in case 1, so the overall noise that you get from the circuit will be smaller when you choose a higher value of GM and a smaller value of this load resistance RL. And again, since again RL is in numerator, GM is in denominator, so it makes sense to choose a higher value of the transconductance and lower value of the load resistance to get overall better noise performance. So one can also argue in this case then why not to go all the way and make GM as a very high number, as let's say some 40 millisiemens or 400 millisiemens, and RL as a very low number. What will be the problem in that? Well, the problem in that will be the GM that we make over here is like the GM we get in a transistor. So we know that in a transistor we have the current equation as ID is equal to mu n Cox W by L, half mu n Cox W by L into VGS minus VT whole square. And if we want to find GM in terms of ID, so GM is basically proportional to square root of ID. ID is the current that is flowing through this transistor. So if we try to increase GM to a very high value, we will have to increase this current to a very high value. In that case, what will happen is the power consumption that we will have to supply to this thing will be immense. So basically, we what we see is if we try to increase the value of ID to get a higher value of GM, we the noise basically reduces. So we are burning more power in order to get lower noise from the circuit. Understood? So we need to hit a sweet spot that there should be a sweet spot where we are not consuming too much amount of power, or we are not generating too much amount of noise. So at that sweet spot we must keep our power and noise constraint. So there can also be a way in order we can find this sweet spot. So let's say I'm worried only about this id. So I am worried that this whatever ID I will get, like the this will give me proximity of how much power I am going to consume. Okay. So and I know that GM is basically root 2 mu n. So we'll verify, we'll derive this equation. So ID is half mu n Cox WL VGS minus VT whole square, and GM will be mu n Cox W by L into VGS minus VT. So this is equation 1, this is equation 2. If we square the equation 2 divided by equation 1, so we get GM square by ID is equal to 2 mu n Cox W by L. Hence, GM is equal to 2 mu n Cox W by L times ID square root. Okay. So this is the value of GM we get. So we can put this value of GM and let's say a gain that we need from the circuit is say A. So what is the value of resistance that we will get? A is equal to GM times RL. So RL is equal to A by GM. Okay. So input referred noise that we derived is 1 upon A times 4 kT eta by GM plus 4 kT. Sorry, there's a small mistake over there. Just a minute. No, it's correct. Fine. 4 kT by GM plus 4 kT by eta. Wait a second. So eta will come in numerator over here. Eta times RL. So this was it, right? 4 kT by RL and 4 kT by RL multiplied by RL square into, yeah, correct. So this is the noise we had, and we can substitute the value of RL in this equation. So we get 1 by A into 4 kT by GM plus 4 kT eta into A by GM. So this is an equation with the GM value we can take out common. 4 kT eta A into 1 by GM. And what is the current that so this is going to burn some current, and if we write GM in terms of current, we get this value. So 2 mu n Cox W by L times ID. Okay, so you can see that if I try to increase the value of the current, that means I am trying to increase the power. Basically, my noise will keep on reducing as Vn is inversely proportional to 1 by square root of Id. Correct. So here we can see that the power and noise are inversely proportional to each other. So you can burn more power to get lesser noise, or you can reduce power and pay the penalty in noise. Any doubts in this? Okay, so we will move forward. So we discussed uh, a common source amplifier, that was this thing, V out. So now other thing that we were discussing about it is input referred current noise source. Now input referred current noise source will be zero. Can anyone tell why input referred current noise source will be zero? Yeah, so since it was open circuit, so we found that the transfer function from input current to output is infinite. And if a transfer function from input to output is infinite, and to find out the output current source, find out the input current source, what we do is we divide the whole thing by the transfer function squared. So we will be dividing the whole thing by 1 upon infinity by infinity squared. So we will get uh, input referred current noise source as equal to 0. So Vn in this circuit is 1 upon Gm RL into 4 kT by Gm plus 4 kT eta times RL. And In in the same circuit is 0. So this was the treatment done for the common source amplifier. Now another variation of common source amplifier is a cascode amplifier. So are you guys familiar with cascode amplifier? Are you guys familiar with cascoding? Okay, so why cascoding is done is the cascoding is done. So let's say this. So in this problem, we assumed the output resistance of this transconductor to be infinite. However, this won't be the case always. So if the output resistance of this transconductor is a finite value, we will see what happens with the whole circuit. So in that case, we use a cascode transistor. So how does a cascode transistor work? So we give input over here, and this is set to some biasing voltage, and we take output at this node. So if we look in impedance from this node from here, then the impedance that we were looking, so let's say this was Z1 and this is Z2. So Z2 will be much higher than Z1. In analog circuits or analog electronics class, you would have learned that if the Gm is the transconductance of both the transistors, and out Ro is the output resistance of both the transistors. So in that case, the Z1 will be equal to R out itself, and Z2 will be equal to Gm R out whole square plus R out plus R out. So this is a result that you would have derived in analog electronics class or analog IC design class. So let's try to analyze the noise for this circuit. Okay. So we will proceed in the same way. So now in small signal case, this VDD and this VDD and this V bias will be AC grounds. These can be considered as ground while analyzing the small signal case. So let's try to draw the small signal. So we have a GM over here. So again, for now, the for this analysis, the we will assume that the output resistance of the transistor is infinite. So let's say V in is applied over here, and then we have this is GM times V in. Then we have another current source over here as GM. Let's say this is Vx, and this is a ground. So this is GM times 0 minus Vx, and this can be written as minus GM times Vx. Okay, and then we have this resistance RL. Okay, so again, the what will be the input referred current noise in this case? I think this is straightforward. Yeah, input referred current noise in this case will again be zero, because the input resistance is infinite, and the transfer function, the current transfer function from input to output will be infinite. So we will only focus on the input referred voltage noise. So first of all, we will find the transfer function from the input to output. So the current that is flowing in this direction, the current that is flowing here, what will be the current that will be flowing? This will be GM times V in. Now, does the current has any path other than this to flow? So what will be the, so can you guys tell what will be the current that is flowing in this direction across this value RL? If GM times V in is the current flowing through this voltage controlled current source, what will be the current source that is flowing through RL? So the current source that will be, so the current that will be flowing through RL will be same as GM times V in. Why? Because the current has no other path to flow other than this complete path. So according to KCL, the Kirchhoff's current law, the current that is flowing through this no, this resistor, the load resistor, will also be GM times V in. And so the voltage here Vx will develop accordingly. So the voltage over here will since GM times V in current has to flow through this transistor, so the voltage that will develop at this the voltage Vx will be equal to minus V in. And why it is happening? Because this cascode thing over here, it is kind of providing negative feedback to this cascode transistor, and negative feedback is basically making sure that the current the to make sure that the current that is flowing down and the current that is flowing up is equal, so that the node voltage doesn't blow up. It will set the node voltage at the desired value, and in small signal case it will be equal to whatever input voltage, the negative of whatever input voltage that you apply. So The current from here will be Gm times Vin. And if the current from here is Gm times Vin, so output is again minus Gm times RL times Vin. So the H equivalent voltage transfer function is equal to minus Gm times RL again. This is the same as the previous one. So now we proceed to find the noise of various the output noise power spectral density due to various noise sources. So how many noise sources will be there in this circuit now? Yeah, there will be three noise sources, two from the transistor. One is the input transistor, other is the cascode transistor. So we will see how to find the noise from each of the transistors. So first of all, we will go for the input transistor as well only. So I will copy this circuit. So we will find the noises one by one. So since this is a linear circuit, so superposition is valid. So first of all, now we will find the noise output noise. So first of all, we will this is 4 kT eta times Gm. Okay, and now if this noise source is this voltage is de-energized, so since this current is Gm times Vin, so and Vin is equal to 0, so in this case this current source can be removed. Now there is only a noise current source from here. Again, there will be no path for the circuit, no path for the current to flow elsewhere. So all the current will flow through the resistor itself. So the noise at the output due to this particular noise current source will be 4 kT eta times Gm into RL squared. Correct. Now, noise for this particular noise source has been found out. Understood? Now, we will try to find it for the resistor. This is minus Gm times Vx. Here is RL. Here is the four kT times RL. Okay. So again, uh, can you people tell so now this 4 kT times RL can flow either in this direction or in this direction. Okay, now if any of this 4 kT RL times 4 kT times RL flows in this direction, it has no path for it to come out since here it's an open circuit. Okay, so no current will flow in this direction as the current flowing in the downward path is 0. So all this 4 KTRL will flow into this resistor. Hence, sorry, this is 4 KT by RL. So the noise due to this RL, noise current source for due to RL will the output noise will be V out is equal to 4 KT times RL into sorry 4 KT by RL into RL squared. That comes out as 4 KT times RL. So we have found out the noise due to the input transistor that was 4 KT eta times Gm, and we have found out so can you unmute and explain your doubt clearly, like from which part you couldn't understand? Just a minute. Uh, from my side, it's open. Okay, there might be some issue on your side. So I will try to explain it again. So this you understand, right? That there will be the output, the noise source of a resistor can either be considered as a voltage source in parallel to that resistor, or a current source, sorry, voltage source in series to that resistor, or a current source in parallel to that resistor. This you understand, right? Okay. So this part I hope you understand. And now this current has to flow either, there are two paths for this current to flow. One, it can flow in this direction, other, it can flow in this direction. If any of this current had to flow in this direction, let's say I, okay, and then it will flow like this. And what is the current that is flowing over here? Since it's open circuit, so I has to be equal to 0, because whatever current flows in this direction has to come out from here, and there is no path for the current to come out from this open circuit. So no current can flow in this direction. Is this clear? Understood. So all the current will flow into this resistor. Now, if the current, all the current flows into this resistor, what will be the RMS? So this is not. So this is okay. I should change this notation. So it's not basically the output noise voltage. It's output. It's power of the output noise voltage. So what will be the power of the output noise voltage if all the current, not mean square, yeah, correct, mean square, mean square of this. So it will be 4 KT, 4 KT by RL, that is the current flowing in this, multiplied by the transfer function square. Now, what is the transfer function from this current to this output voltage? It is RL times, it is RL, and its square will be RL square, correct? So what we will have is the current, that is the current's power, that is 4 KT by RL, times the transfer function square, that is RL squared. So overall we have 4 KT times RL. Is it clear? Understood. So now there is the last is the noise from cascode. So noise from cascode, how we are to proceed for that? So So noise from cascode will be in parallel to this current voltage controlled current source. And what will it be? Its value will be 4 kT eta times Gm. Okay. Now, how to find the overall current from this noise? Uh, how to find the output mean square voltage due to this current noise source? So again, this particular current can only flow upwards, right? Are you able to understand this? Because there is open circuit downward, so this noise current can only flow in upward direction. And since it can only flow in upward direction, so what will be the current at this point? That will again be 4 kT eta times Gm. Now 4 kT eta times Gm is flowing in this direction. Hello. Yeah, Talpasai, now you are audible, I think.
Yes, sir.
Yeah. So, okay, I will proceed for now. If there is doubt, you can ask. So now all this noise all this noise current since is flowing. Uh, Talpasai, you can mute yourself until and unless you have to ask some. There is a feedback due to your voice, so please mute yourself. Yeah, thanks. So so what I was saying was that all this noise source, all this noise cannot flow in this direction as it is open circuit. So all this noise will flow upwards. And since this is a single path, so all this noise will come in this direction. So 4 kT eta by 4 kT eta Gm is in this branch. 4 kT eta Gm is in the lower branch also. Talpasai, again, you are not muted. Please mute yourself. Thanks. So what will be the current that will be flowing in this load resistor? The current that will be flowing in this load resistor will be equal to zero. Okay. So we see that no output voltage is developed due to this current source. So the contribution from this cascode current source is zero. Is this clear?
Yes, sir. Next class.
Yeah. So what we have over here is in this circuit, this is V in, this is VB. At output, we have V naught. So in this complete circuit, the noise current, as far as noise is concerned, this circuit and this circuit are equivalent, provided that the output resistance of this transistors are considered to be infinite. So in this case, the noise contribution from the cascode transistor, its noise will be equal to zero. Okay. Now, in what case the noise from this transistor will start coming into the circuit is, let's say there was some output resistance over here. There was some output resistance R naught. In that case, what will happen? All the current won't flow in this direction. There will be some current that will be flowing in this direction as well. So the current that is coming out will be lesser than 4 kT. Okay, I'll draw it in separate color. Just a minute. let's say there was some R naught over here. So there will be some current flowing in this direction. So the current that is flowing in this direction will be lesser than 4 kT eta times Gm, and this will be lesser than 4 kT eta times Gm. Now, since the 4 kT eta times Gm is flowing into this current source branch, so there will be some amount of current that will be flowing into the load resistance as well. So if there is some output resistance present for the input transistor, so in that case there will be some current due to some noise contribution from the cascode, but it will be much less significant as compared to the noise that is coming from the input transistor and the load resistance. However, at higher frequencies, what will be the case? There will be some parasitic capacitance at this node. Now, as the frequency keeps on increasing, the impedance that we are seeing due to this parasitic capacitance will keep on reducing and reducing. That is equivalent of saying the impedance that we are seeing in this node, Vx node, will keep on reducing and reducing. So what will happen is, in that case, the cascode noise will again come at the output resistance. So we can conclude that cascode noise is insignificant at low frequencies. Is it clear? But as the frequency keeps on increasing, if the impedance at the impedance of this node keeps on reducing and reducing, and hence the cascode noise current will also come into picture. So is this thing clear?
Yes, sir. So for high frequency, means we need to uh, replace one cascade,
Sorry,
cascading techniques.
come again.
For a high frequency, the parasitic capacitance and resistance will come into picture, no, sir.
Yeah.
At the time, what we will do, sir, for noise?
So, as far as noise is concerned, you need to size this cascode transistor in such a way that, till the frequency of interest, you are not, the noise from this transistor is insignificant. You can increase the GM of this transistor by having a higher size of this transistor. This you can do. Apart from that, if that is not working, the noise from this transistor is still significant. So in that case, other thing that you can do is, like, instead of so basically, why you are having this cascode over here? The purpose of having this cascode in the first place was to increase the gain, because the gain, when in what case the gain will reduce, if there is some output resistance R naught in R naught over here. So R naught will come in parallel with RL. So if this is the case, if the gain you wanted was GM times RL, you won't get GM times RL. However, you will get GM times RL parallel R naught. So to remove the effect of this R naught, this cascode was installed in the first place. If the noise of the cascode is still a problem, you can, instead of having a single stage and having a cascode in that, you can go for 2 stages or 3 stages to get the desired gain. But
Sir, at
generally,
the time, oh, okay.
yeah, but generally what happens is, you will try to increase the size of this transistor. If you increase the size of this transistor, the transconductance of this transistor increases, and in that case, the noise contribution from this noise source will basically reduce. So why I am saying that is, we can do a high level analysis of that. So we saw that there is some 4 kT eta times GM noise coming from this transistor, right? So if there is some output resistance over here, there will be some alpha times 4 kT GM noise that will be flowing in this load resistance, and the voltage developed at this will be some alpha times 4 kT times RL squared. And if we see the input referred noise of this complete circuit, this will be divided by basically the GM of the input transistor, that is, let's say we call it GMI whole square. Uh, this was GM itself. So in this case, we see that again it's inversely proportional to 1 by GM. So with this, we can show that if we size these two transistors accordingly, we can reduce the overall noise from the circuit.
Thanks.
Okay. So we can extend this same principle to differential circuits as well. So we have seen we have seen single-ended circuits only. So we will try to do it for differential circuit also. So let's say now we have this thing over here. We have one RL, GM, and this gives us VI plus, so V common mode plus VD by 2. We have some GM2 over here. We have GM, V common mode minus VD by 2. So this is the differential pair equivalent of the common source amplifier that we saw. So how we will go about finding the noise source, the input referred noise. So in this case, an easy solution for this thing is so basically we can either find the common mode, the output voltage noise power, or we can find the short circuit current noise power. And in that case, what we will have to do is we will have to find the transfer function from input to the short circuit current, and then find the noise power that is going into this short circuit, and then divide the two. Okay, so we will try to follow that thing. So in differential, what we will have is this, let's say this is I out, this will be minus I out. Okay, so the voltage, the current, the gain that is there from this input to the output, what will it be? We can find it like this. So there is some voltage VD by 2. There is voltage minus VD by 2 over here. So we will ignore the common mode voltage, as this is a differential circuit, and we are assuming the tail resistance, the output resistance of this transistor to be infinite. So this resistance can be ignored. So the common mode rejection will be infinite. So we will just focus on the differential uh, aspect. So so are you familiar with what will be the voltage at this node?
Zero, sir.
Yeah.
Balance.
So in the differential mode operation, since this is a common node for this differential half circuit and this differential half circuit, the details you will understand in analog IC design. So for due to that, the voltage at this node will be 0. Okay. So So this again, the noise, the gain from this input to the short circuit output current will be, so short circuit output current can be written as this current can be written as IO is equal to VD by 2 into GM. Okay. Why? Because since in differential half circuit, this voltage is 0, this voltage is VD by 2. So the current that will be flowing is GM times VD by 2. And since this is a short circuit, so all current will flow in this short circuit. So the current I out in this branch will be GM times VD by 2. Similarly, in the other half, since it's minus VD by 2, so this current will be minus GM times VD by 2. And their subtraction will give us overall differential output current. So IDIF will be equal to GM times VD. Okay. So we have, so the gain IDIF upon VD comes out to be GM. Now what we are to do, we are to find out the noise power that is going into the short circuit by de-energizing the input voltage sources, and then we will divide the total output noise power by the by this uh, gain that we just found out, that is GM. Okay, so the noise power, if we see, we have an RL over here, an RL over here. This is GM2 and this is GM. So noise due to this RL resistor will completely flow again into this short circuit. So from here, there will be 4 kT RL that will be flowing in this node, and in the opposite node of this, again there will be 4 kT RL. So now since this resistor and this resistor are independent of each other, so the noise that these two things will be producing will be uncorrelated. So the total noise that we get in this will be since even though we are taking the difference of the current in this and this, but since these two currents are uncorrelated, so their powers will so we will have to so the overall power we will find out by adding the power of the two, since the cross correlation between the two is 0. So the I out will be 8 kT times RL, 8 kT times RL, sorry, it's again 8 kT by RL was the current source, 8 kT by RL times, so this is 8 kT by 8 kT by RL.
Sir, sorry for interrupting, sir.
Sorry.
Sorry, you're telling me about unbalanced output, right, sir? That's why
Uh,
that noise is uncorrelated.
the
That's
noise
the
is
reason, sir.
uncorrelated because the noise sources are the noise is coming from two different sources, with both of them are two different random processes, so they will be uncorrelated to each other.
Not because of unbalance.
No, it has nothing to do with unbalance. There is no unbalance in this. Both of the input is so what I am doing is I am putting a noise source in both the branches, right? It's 4 kT by RL and this is 4 kT by RL. Now this noise will directly flow into this short circuit. It won't travel below. Okay, because this is anyways infinite output impedance of this transistor. So, and this is a zero output impedance. So all the noise will flow in this short circuit only. And the same thing will happen on the right side as well. All the noise will flow into the right side short circuit. But and the differential current that we wanted to find was, let's say we call this side as N and this side as P. So was sorry, we will interchange the notation. This side as P and this side as N. So the differential current was IP minus IN. Now, since this is a random process, that is 4 kT, this random process has a power of 4 kT by RL. This random process also has a power of 4 kT by RL. And these two random processes are uncorrelated with each other, so their powers will be added. That's why we will get 8 kT by RL. Is it clear?
Yes, sir. Yes, sir.
Okay. So, since the same thing will happen with the noise source of these two input transistors as well. So that will become 8 by 3.
Sir, to minimize the noise, here there are only option is we have to increase the value of RL.
No, no, you should not increase the value of R. This is the output noise power. This is the output noise power. We have still not found out the overall input. If we have still not found out the overall current, overall the gain from input
Iode
to
by
output. Yeah, the input noise. We need not to minimize the noise power in itself. We need to minimize the signal to noise. We need to maximize the signal to noise ratio. Okay, and to maximize the signal to noise ratio, what we look at is the input referred noise. We have still not found the input referred noise. So this is just the output noise that we had, and the same thing we will have over for the transistor GM as well. That will be 8 by 3 kT times eta times GM. Okay, so overall output noise current, since we are finding out the short circuit current, will be, sorry, this will be 16. Mm, oh, since we are having this eta as well, so this will be just 4 kT eta times EM. So what we will have is overall, since this became double by 4 kT, 4 kT by RL and 4 kT by RL, the noise from these input transistors will also become double. So that will be 8 kT eta times GM plus 8 kT by RL, and this will be divided. And what will be the noise due to this transistor? So noise due to this
which one?
transistor, the lower transistor, the tail transistor.
It will be addition of P and N, sir. Current will be added.
No, in this case, yeah. So this is one more point in for the noise from these two transistors and noise for these two resistors. These two are separate random processes, so they will be uncorrelated to each other. Correct. But noise from this particular tail current source, what will it do is, so let's say there is 4 kT eta times GM over here. So it will, so now these two circuits are symmetric. So what will happen is this 4 kT eta times GM will, so whatever noise current this gives, IN, will divide itself equally into both the circuits. So both will just come out of this short circuit that is present. Now this division has happened of a single the same random process. In previous cases, there were two different random processes that were going into the respective nodes. But now the same random process has been divided into two, and that is going into these P and N nodes. So they will be completely correlated to each other. Okay, so there you should not add power, there you should add voltages. And in this case, since this is IP minus IN, you will subtract voltages. And since the circuit is symmetrical, so the current will be divided in half. So the short circuit current in both of them will be equal and opposite. So the current contribution due to this tail transistor will be zero. Is it clear?
So how it would be zero, sir?
So this you understood, right? Like this will be
Yes,
4
sir.
KTRL, 4 KTRL. These are uncorrelated, so they will be added. This you understood, right?
Yes, sir.
Yeah. Now, in case of the tail current source, in case of tail current source, what will happen is, let's say this is IN. This circuit and this circuit are symmetrical to each other. Symmetrical. You understand this, right?
Yes, sir.
Yeah. And this IN can flow either in this direction, or this direction. Correct?
Yes, sir.
And will any component of IN flow in the transistor below?
No possibility, sir.
Yeah, because this is open circuit. So the current will flow in this and this direction only, right? Now, since these two circuits are symmetrical, so the impedance that this will show and impedance that this will show will be equal to each other, right?
Yes, sir. It will be identical.
Yeah. So this IN will divide itself in IN by 2 and IN by 2. Correct?
Yes, sir. Yes, sir.
And the same IN by 2, since there is no other path for this IN by 2 to flow, it will flow through this transistor. Yeah, it will flow this through this transistor, and this will be IN by 2. This will be IN by 2. Is this clear?
Sir, could you, means, after the transistor, I am not getting, so IN by 2, IN by 2. Repeat this point again,
Yeah.
sir.
So this IN by 2 will flow through this transistor. There is no other path for this IN by 2 to flow. And then again, it has to divide it either in RL or in this short circuit. Now, this is short circuit, it is zero impedance path. So all this IN by 2 will flow in this short circuit.
Okay, okay, sir. Yeah. It is flowing through short circuit, right?
Yeah. Now, previously, what was happening is the noise power in this branch was 4 kT by RL. The noise power in the other branch was 4 kT by RL. And since those two noise powers were being generated by two different sources, so they were uncorrelated to each other. Okay. But in this case, what is happening is the same noise source is being split into two, and the noise here is IN by 2 and noise here is IN by 2. So previously they were uncorrelated, so you added the power. Now these two noise sources are correlated. They are not uncorrelated. So here you will add the voltages. Sorry, here you will add the actual quantities and not the power. Here you will add the currents. Are you getting this point?
Yes, sir.
Okay. Now, from addition, basically, I mean, not the addition. This is IN. If this branch is, let's say, capital P, and this branch was a capital N. So what was the current? That was IP minus in, right? And now since you are only worried about the actual value of these currents and not their power, so it will be in by 2 minus in by 2, unlike the previous case where you were adding the power. Now these are actual quantities, not the power of them. Are you getting this point?
Yes, sir. Yes, sir.
Yeah, so in that's why the noise contribution from the tail current source will be zero.
Yeah. Okay, sir. Okay, sir. Thank you, sir.
Okay, so now you have value of I naught as 8 kt eta times gm plus 8 kt by rl, and the value of this thing, and the no, the transfer function we found as from input differential input to differential current as gm. So we can again do the same exercise over here. So what we will get is input the input referred voltage noise will be 1 by gm square into 8 kt eta times gm plus 8 kt by rl, correct? Now again we can take out rl square common. We can divide and multiply it by rl square and rl square. Okay. So what will happen is we will get gm square rl square into 8 kt eta. Now this is gm times rl square. So you can write it as gm square by gm. So we have just a minute. Uh, was gm. So if it goes in, so if we take this gm square inside this bracket, so it will become 8 kt eta by gm plus 8 kt gm square times rl. Okay. Now this gm square times rl is what? So we can multiply and divide it by rl. So it will become rl square in the denominator and rl in the numerator. And this gm square times rl square is the gain square. So it becomes 8 kt eta by gm plus 8 kt upon the gain square into the load resistance. So the conclusion of the common source amplifier and this differential amplifier is same, that the input referred noise is directly proportional to the load resistance and is inversely proportional to the transistor. So if you want to increase the noise factor, or you want to increase the signal to noise ratio at the output of this amplifier, you need to increase the value of transconductor, and you need to reduce the value of load resistance. But if you do that, you will have to pay, you will have to burn more power in the circuit, as we saw in the common source amplifier. Because again, here GM will be proportional to the square root of the current that is flowing through it. And again, to increase the GM, you will have to increase the current and burn more power. Is this clear?
Yes, sir. Sir, means we have to scale this value, sir. It means for power and for noise, we have to scale the values, right?
Yeah. So if you want low power, you will have to pay the penalty in terms of noise. If you want to have low noise, you will have to burn more power.
Next up, sir. Thank you, sir.
Okay, so any other doubt? So this was about it from my side for today's tutorial. Any other doubt from your side?
Yes, sir. Sir, if we are designing any circuit, we have to check from week three. We have to scale full swing voltage, how much full swing voltage, and in terms of noise, uh, up to which voltage we have to regulate like this, no, sir.
Sorry, I couldn't understand your question.
From week three, if you want to design any circuit or op amp, we need to get a full swing voltage and noise also very less, no, sir. We have to take care of full swing voltage and noise voltage. Could you relate and tell me entire picture, sir?
So, see, full swing voltage depends on. So you will scale. You will first dynamic range scaling. You will do. So, dynamic range scaling will help you achieve maximum signal power that is possible at each node, right?
Yes, sir.
Yeah. So maximum. If maximum signal. So let's say there is a node, internal node, let's say call v out, or let's say, okay, let's say we call this internal node as some v1. Okay, and the input is v in. So you have achieved maximum gain that is achievable to not to saturate this voltage. That is what dynamic range scaling is, right?
Yes, sir. Before saturation, we have to. Yes,
Yeah.
sir. Exactly.
So there is some gain from the input to this internal loads, let's say A. Okay.
Yes, sir. Yes,
Uh,
sir. I'm listening, sir.
yeah.
I'm mic is
Yeah.
on mobile, sir. Noise is coming. That's why I'm waiting, sir.
Yeah. There is some gain from input to this node called A. Okay. Now there will be some noise that will be generated by this by this component. Let's say some n square. Okay. Now the input referred noise will be something like n square by a square, correct? So if you choose A in such a way that the voltage swing at this node is maximum before the saturation, so what you are doing, you are maximizing the value of A. In that process, what you are doing, you are minimizing this quantity, that is the input referred noise. Okay, so dynamic range scaling basically directly relates to having the maximum signal to noise ratio or minimum input referred noise possible in the circuit.
Yes. Sir, sir, from week 7, sir, a deadline is completed. Sir,
Uh, yeah,
while we are considering input noise, we need to consider the gain, sir.
yes, you need to consider the gain. The gain from input to output will only the square of that gain will only be divided to get the input referred noise, right?
For output noise, for input noise, what is the variation, sir? I'm not getting the point.
The output, the noise in itself doesn't has any significance. Let's say there is some noise power at the output. For some circuit, it's let's say 2 microwatt. Some other circuit, it's let's say 4 microwatt. Okay, but the signal power at the output of circuit 1 is, let's say, some 8 watts. So I will compare it just a minute. This is circuit 1. This is circuit 2. Okay. The noise power at the noise power is, let's say, 2 microwatt. The noise power here is, let's say, 8 microwatts. So if you just look at the output noise power of these two circuits, what will you say? Which circuit is better?
Absolutely 2 microwatts, sir.
Yeah. So you will say circuit 1 is better. But now let's say I say that gain from input to output for this is, let's say, 8, and gain from input to output for this circuit is, let's say, only 1. Okay. And say there is a 1 watt input I am giving to both of these both of these circuits.
In this case, second case is better, sir. 8 microwatts is the best case because 1 microwatt with one gain.
Sorry, just a minute. Let me interchange the gains. Let's say gain for circuit 1 is 1, gain for circuit 2 is 8. Okay. So in this case, the signal power at the output will be 16 watts. Okay. But the signal power at sorry, not 16, 64 watts. But the signal power at the output of circuit 1 will be only 1 watt. Okay. Now, if you take the ratio of these two, if you take the ratio of the signal power by the noise power, in circuit 1, it will be 10 to the power 6, 0.5 into 10 to the power 6. While in circuit 2, it will be 8 into 10 to the power 6. So you see that circuit 2 is actually better, even though the absolute output noise power for circuit 2 is higher, but since the gain from input to output is better, so circuit 2 is better. Okay, now instead of doing all this story, what you could have just said is that I won't apply the signal and then check its output power and then divide the signal power by noise power. What I will do is I will just divide the output noise power of both the circuits by their respective gains. So in that case, the input noise power for circuit 1 will be, input referred noise power for circuit 1 will be 2 microwatts only, while for circuit 2 it will be 1 by 8 microwatt. Okay, so you could directly, instead of applying a signal and then checking that whether circuit 1 and circuit 2 which of them is better, you can directly say by looking at the input referred noise power that circuit 2 is better. So this is what input. So this is the significance of input referred noise. It is basically to compare two circuits with different transfer functions and all those things.
Yes, please. One more thing, sir. I will ask.
Yeah. So are you asking something, Talpasai?
Yes, sir. Yes, sir. 1 minute. I'm going for it. Sir, my question is, if you want to find out the noise voltage spectral density, input preferred noise spectral density, and output preferred noise spectral density with examples, sir.
So that example is already there, no? You have done it in the assignment, I guess.
Yes, sir. But I'm not able to differentiate, sir, input and output. If I commit mistake, means I will.
You are not able to differentiate, as in I don't understand. So let's say
No, no,
there
no.
is this thing, there is this RC thing. Okay, this is the input, this is the output. Okay, now you want to find input referred voltage noise of the circuit, and also input referred voltage power spectral density and output referred voltage power spectral density. So for first of all, what you will find the output referred power spectral density. Find the output PSD. Okay, what will be
Yes,
the
I will
output
find out
PSD?
V out by Vs, 1 by
No,
uh,
no, output PSD, not V out by Vs. Output PSD will
of
be
4 kT R into HF square, no, sir.
4 kTr divided by 1 plus S square by S square into R square into C square. Correct?
Yes, sir. Yes, the transfer function.
Yeah, this is the output PSD. Now, what is to find the input PSD? What you will have to do?
With respect to input, we have to find out, sir.
Yeah. So first of all, you will find the transfer function from input to output. Correct.
Yes, sir.
So what is the transfer function from input to output? It's 1 upon 1 plus
One.
S times RC. So this will be omega. Just a minute. S times RC. This is the transfer function from input to output. What will be its h of j omega magnitude whole square? That will be equal to 1 plus omega square r square c square. Correct?
Yes, sir. Yes, sir.
Okay. Now
Sir,
SV
here
in
I
out.
get a doubt, sir.
Yeah.
Sir, here imaginary term is present. That's why you are finding the magnitude, sir. If it is real term, no need to find out the magnitude.
In that case, magnitude and actual value will be same. Only it's
Yes, sir.
like if sign is like let's say it's -1, its magnitude will be 1.
Yes, sir. Yes, sir. Correct. Yeah.
Yeah. So SV in will be SV out divided by h of omega whole squared. Correct?
Yes, sir.
So this will be 4 kTr upon 1 plus omega square r square c square into 1 upon 1 plus omega squared r squared c squared. Okay. Do you follow this?
Yes, sir.
So,
Sir, could you please repeat again, sir? SV out by H omega square
sorry.
4 kT. Could you repeat again that S step again, sir?
So this you understand, right?
Yeah, sir. Next one, sir.
Yeah. So SV out we saw is 4 kTr into 1 plus omega square r square c square.
Yes, sir.
And
This one. Next, how that came 1 by 1 by omega plus omega
this is
square.
so this is 1 upon h omega square, right? So 1 upon the h omega
So it is
magnitude of,
multiplication, no, sir.
yeah.
Oh, okay. I thought it is addition, sir. That's why I'm asking.
Okay. So this is just 4 kTr. So your input referred noise power spectral density is 4 kTr, while your output referred noise spectral density was 4 kTr times 1 upon 1 plus omega square r square c square. So is it clear?
Yes, sir. I get it. My answer is also correct only, sir. Yeah. Good.
Yeah. Any
Sir,
other doubt?
1 minute, sir. 1 minute. 1 minute. Sir. I will check it. Yes, sir. Nothing for this week, sir. Sir, could you please refer any book, sir, to practice the problems? Is there any way to practice, sir? I'm
This
appearing for main exam also.
yeah, Behzad Razavi has a very good number of problems on noise. You can refer to that.
Yes, that is CMOS also.
Yeah, the CMOS IC design book by Behzad Razavi. You can practice questions from that.
Sir, for week 3 and week 4.
So week 3 and week 4 are mainly this filter design and all those things, right?
Yes, sir.
So this you can so those are mainly practice about finding transfer functions and all those things. So those can be done, I think, by this linear circuit analysis book we have from Hyatt and Kemmerly. You can use that.
Sir, could you comment section, sir? I will copy it. Second for both, sir.
Just a minute, I will. So this is the book that you can refer to for solving questions regarding op-amp transfer functions and all those things. So
Sir, this one only, sir, for week 3, week 4 also.
yeah, you will find a lot of material practice in this.
William Hyde. But it is electrical circuits, no, sir.
Yeah, but see, the main thing that you need to work out in week 3 and week 4 is finding transfer functions and all those things, right? So
Yes,
here you will have chapters on these circuits. The active RC filters and active RC circuits are there. There is a whole chapter dedicated to that, so you can practice from there. Apart from that, you can just use your simulator, generate your own, and whatever circuits you see in those in this book, you can put it in the simulator and check its transfer functions and all those things.
sir, for analog circuits also I refer one bit, sir. Boylsted.
Sorry, Boylsted.
Boylsted, sir.
Yeah, Boylsted is also okay. Apart from that, you can refer to the Microelectronics by Cedra Smith, or other book is this Behzad Razavi also will work for analog circuits as well.
Sir, is there any differentials between analog IC and digital IC careers?
Sorry?
Means the career path is different, sir, for analog IC
Yeah.
design engineer and
Yeah, digital IC design and analog IC design are completely different fields. So in digital IC design, predominantly there is a lot of automation in digital IC design. So there, you are mostly working on these Verilog and all other Verilog, and then synthesis, and then physical design verification and all those things. The analog design, or even high performance digital also, is mainly custom IC design. So there you actually design the circuit, the size each transistor by itself, and then age up and all those things. So these two are completely different.
yes, sir.
Okay, so any other doubt?
Nothing, sir, for this week. So fine.
Okay. Thank you for joining.
Thank you.